Hi, we're now going to look at Lesson 5, Elastic and Inelastic Collisions. And this is really about following definitions to figure out how we categorize collisions as elastic or inelastic, and then how to mathematically test a collision to see for sure if it falls into one category or the other. Now, a few things that I do want to mention to you about elastic versus inelastic collisions before we start anything else. First of all, this is not momentum. One of the problems is that, here we are at the end of chapter 9. We've just been doing all this momentum stuff, including collisions, and people think that this is the same stuff just kind of continuing. We're not going to use any momentum stuff in these problems. Do not use P equals mv. Don't say, oh, I'm just going to solve for a 2D collision or something like that using my momentum methods. That is not our purpose here. Also, because of previous things you've learned, sometimes people will run to things that they heard about for elastic objects and elastic potential energy. But we are not using Hooke's law. It's not that stuff. We are not using the elastic potential energy formula. That is not what is going on here. So yes, it is still the idea of elastic objects, things that can hit and bounce back to their original shape, but we're not using physics 20 ideas for this. The best news I've got for you that I clicked on by mistake there quickly for a second is we're not going to be using any angles. Most of what we've been doing in this chapter is so very driven by, is it 1D, is it 2D, break it into components, pay attention to the directions, all that stuff. Now, the good news I can tell you is no angles. So yay, no components. There's a lot of what I'm saying here that is to try to tell you not to use the wrong things and to not make this more complicated than it needs to be. What we're basically doing is going by definitions of why a collision would be elastic versus inelastic. Elastic collisions must involve like microscopic level things hitting each other. And that's because in a room like this, as air molecules are moving around, they're bouncing off of each other randomly, they're hitting the walls, all that sort of stuff. All of those collisions must be elastic. Because if they weren't, if energy was wasted, lost in all of those collisions, well, where would the energy go? And eventually then all the particles in this room, the air particles, would just end up stopping. We'd hit like absolute zero or something. That's not happening. As the air molecules bump into each other, hit the walls, hit me, those collisions are perfectly elastic. No energy is lost. So that as they hit me and bounce off, they must bounce off with the same velocity and therefore the same kinetic energy as they originally hit me with. And that is really, really the focus of what we have to look at when we're trying to figure out if a collision is elastic or not. We should be able to take the kinetic energies of, well, for our purposes, like two objects hitting each other, take their individual kinetic energies before they collided, take their kinetic energies after they collided, look at those sum totals before and after, and they'll be the same totals. Maybe one of the objects lost some energy after the collision, but then the other one will have gained that kinetic energy so that the totals stay the same. That means that no energy, kinetic energy of the movement of these objects was lost during that collision. This only happens though at a microscopic level, like air molecules bumping around in the room or something like that. Macroscopically, we have inelastic collisions. When cars hit each other, or when you fall on the floor or walk into a desk or something, those macroscopic collisions will always involve some lost kinetic energy, some energy that is wasted somehow. Doesn't mean destroyed, but it's no longer kinetic energy. So in that case, if it's inelastic, we would take the total kinetic energy of all the objects before, we take the total kinetic energy of all the objects after, and they won't be equal. Typically what we're going to see is that after the collision, there will be less kinetic energy because energy has been lost to the environment. But this is really the mathematical test that we use. We look at all the kinetic energies and we see if before and after kinetic energy was conserved. Not just saying conservation of energy, because that includes all the different kinds of energy. It must be exclusively must be the kinetic energies that we're only looking at. That's it. But that is great for us because kinetic energy, being scalar, doesn't have directions. So nothing about the directions matters. Not even stuff like left and right. It's just kinetic energy. That's it. So as an example of testing this, because if a question ever says, determine if the collision is elastic or inelastic, you have to do a mathematical check. Just saying, oh, it's macroscopic. No, that's not good enough. That's an explanation, but you're not determining mathematically. Explain, words. Determine, calculate. Okay, you have to have them separated that way. So I'm going to use the example from the last section of notes, the 2D collision of the red and the blue ball. Now notice here, I'm including the numbers for the blue ball after the fact because we've already done that 2D collision with conservation of momentum. We found these numbers. But now that I've done that, I'm just asking, hey, let's determine if this collision is elastic or inelastic. Now, I can already say, explanation-wise, it must be inelastic because these are macroscopic objects. 1.20 kilograms hitting 2.31 kilograms, those are big objects. These are not molecules or atoms bumping into each other. So this collision is going to be inelastic. That is a description, an explanation of what's happening, but I still want to check it mathematically. So best part again is I'm going to completely ignore these angles. I don't need anything about the directions. I do need masses and velocities because if I'm calculating kinetic energies, that's what I need. I am going to look at the total of what was happening before and the total of what was happening after, but that's it. So I go ahead and before the collision, there's only one object that had kinetic energy, the red ball, because it's the only one moving. I go ahead and I put in its mass with its velocity and I get a number, 175 joules. I know the blue ball has 0 kinetic energy because it's not moving. So this number, the kinetic energy of the red ball, is actually also the total kinetic energy before the collision occurred. Then I look at after the collision. I have 2 objects, both moving, so I'm going to have to do 2 kinetic energies. The kinetic energy of the red ball moving at 13.5 meters per second, and the blue ball moving at 3.66 meters per second. When you're doing these calculations, honestly, the sorts of things that are easy to forget is squaring the velocities, stuff like that. Just be careful about that. It's still 1/2 mv squared, 1/2 mv squared. And I'm adding them because I do want to know the total of the kinetic energies after the collision. Not doing anything with angles though. And I find I've got 125 joules. 175 joules is not equal to 125. I've lost about 50 joules of energy. This collision is inelastic because the total before and the total after are not equal to each other. That's what makes this now determined mathematically inelastic as a collision. One thing to watch out for is, and I'm not saying it works at all with the numbers I have here, but if I had done this calculation and I did all of this and rounds off to 175, and I did my calculation here, and let's say it came out as 174.98. You say, oh, but those numbers aren't the same. Remember, our numbers are only reliable to our sig digs. So if this rounds off to 175, and even though this number might have been different, like 174.9, it rounded off to 175, we have to go with the sig digs. That's all that we can depend on. And it would be saying 175 equals to 175. That collision would then be elastic because the rounded off, paying attention to sig digs, the only things we can trust, that would actually give us our answer. So anytime you're looking at any sort of collision and you're asked to determine if the collision was elastic or inelastic, you do have to do this: kinetic energy calculations. I cannot emphasize that too much. Kinetic energy calculations. The total before and the total after. Basically, you can use this as a test with any of the collisions that you're doing anything with to see if by the numbers they are elastic or inelastic.